Okay, we're going to be looking at the flow of fluids and how they interact with themselves. So the first thing I want to look at is something called volume flow rate. And it's actually quite a simple principle. It essentially says that at any given point, the volume flowing past a given point in a unit time is constant. In other words, if I took a little cross-sectional area here, I'm just going to call that A1, and another cross-sectional area here, call that A2. So here's a pipe, water is flowing, or some fluid is flowing, and you have A1, and then you have A2. Now, for this one here, you end up getting a situation here where the volume that's flowing past here has to be equivalent to the volume flowing past here in a given unit of time. Otherwise, there would be a space between the fluid, and it wouldn't be a continuous flow. And so what we get here is a situation here where the volume divided by the time, again, this is volume, and this is time, that equals a constant. And if you take a look at the units here, volume and time, well, you're going to get a meter squared, a meter cubed per second. Well, there's another way to represent the meter cubed per second, and that is by going the area here, multiplied by the velocity. What you'll see happen here is you'll get a meter squared times a meter per second, which gives us a meter cubed per second back. And so that's another way of representing this, and it's a useful representation here for volume flow rate. What you get here is, if that equals a constant, that means the area here, A1, times the velocity here, V1, has to be equal to the area 2 times V2, and here's V2. What this says is essentially that in a given fluid here, that if the area gets larger, the speed of that fluid must become slower in order for the volume that passes per given second to be constant. And this is precisely why, if you've ever taken your thumb and put it over a hose, it will generally tend to go faster because you've made the area of the hose smaller, and so it compensates by going faster to have the same volume come out through the hose. This formula is quite simple to use. It's basically just a ratio, and so I don't think I need to spend too much time on that one. The other thing I want to talk about today is something called Bernoullis Equation. Now, Bernoullis Equation is somewhat of a useful equation here, in that what it says here is that there's a pressure 1 times rho g y1. Now, y1 is just the height of the pipe, let's say, to the center. And so this plus half rho v1 squared, again, these are rhos, that's pressure. And it equals the exact same thing on the other side. What you'll notice happen here is that as we increase in height, okay, the pressure within this fluid may stay constant. So P1 may be equal to P2 at these 2 points here, at point 1 and point 2. But if that's the case, and we rose a certain height here, that means that it must have sped up along the way. And you'll see that work just like the law of conservation of energy. And that's exactly where this comes from. Essentially, you'll recognize here this looks like mgh plus half mv squared. And then, of course, you got if there's any external pressures on either end. It's a very useful equation in that the higher you go in this pipe, the slower the fluid must flow as a result, or the pressures will decrease accordingly. And so you get something like this. Now, this has some important ramifications, and I'll just explain one of them right now. The first one here is something called Shelleys Theorem. Now, Shelleys Theorem is not something I expect you to memorize. It really is just a branch of the Bernoullis equation. But it looks something like this. If you have, let's say, a bucket of water here, and I'm just going to show a little bucket. I'm going to make a little hole right here. So there's a little tiny hole right here, and here's this fluid. Now, what happens here is that there's a difference in height here, and so we can say, this is y1, and this is going to be y2. Now, this difference in height means that the water is going to tend to be flowing faster down here than up here. But if we remember Bernoullis' equation, and I'll just bring it back here for a moment. Here's Bernoullis' equation. What I do notice here is that P1 and P2 are actually the points right here. Here would be P1. Here would be P2. But if this is a pretty small bucket here, these two pressures are going to be relatively the same. It's essentially atmospheric pressure. So we can eliminate those from our equation. And if we eliminate those from our equation, we get rho gy1 plus a half rho v1 squared, again that's the speed at this point, is equal to rho gy2 plus a half rho v2 squared. Now something else you might notice here is that as the water comes flowing out here, maybe I'll use a different color, as the water comes flowing out of here at some speed, we'll call it v2, we notice here at the beginning that the water's pretty much at rest right here. We're assuming that it's there's no turbulence here for this one here, pardon me. So there's no turbulence. And so what we get here is a situation where v1 is actually equal to 0. And so we can cross that whole term out. And you get an interesting result here. And what you get is essentially that we're going to look at the differences in heights here. And so what you end up getting, I'm going to move this all to one side, but I'll get a half rho v2 squared. This is going to be equal to rho gy1 minus rho gy2. Well, something we can cancel right away is the rho's and get rid of the density. And I'm going to multiply by 2 to bring that across. And what you end up getting here is an equation that says that the velocity at this point 2 will equal the square root of 2 g. And if you look at the difference here of y1 and y2, well, I'm going to say that y1 minus y2, which is what I'll get here, is actually, let's just call it h. And we'll just say that this here is the height from the hole to that beginning. Again, just like potential energy, gravitational, we can pick our reference point, and so we can call that h. And here's our interesting result here. You get this. Now the Bernoullis equation so this is actually this is actually a very good way of calculating the speed when it's coming out of a hole. All you need to know is that h there, just like law of conservation of energy. Now a couple other things with Bernoullis equation is basically, if we look at baseballs do something interesting here. If you think of a baseball that can spin, and so I'm going to make it very, very simplistic and say here's a baseball. Okay, there's a baseball, and the ball is going to be moving that way. So as the ball moves that way, air currents are going to be going along it in this direction. You can imagine the air currents are moving along in this direction. Now if the ball wasn't spinning, not much would happen here, but if we put spin on the ball, and right now I'm going to spin it maybe in the downward direction. So in other words, this ball here is going to be spinning, if you can imagine, it's spinning this way. Okay? It's going to be spinning this way. Well, something interesting happens here. As the air currents go this way, the ball is actually going the opposite direction. And so here, the air currents are actually going to get slowed down. They're actually going to slow down a bit. But here, the ball is moving in the same direction as the air currents, so it'll actually speed up. So if I called this, the air current here V1 and the air current here V2, it turns out that V2 will actually be greater than V1. Well, if we go back to Bernoullis equation, assuming that the pressures are exactly the same here on top and bottom of the ball, it's just atmosphere, or pardon me, that's incorrect. The heights, pardon me, are going to be relatively the same, but the speeds are going to be different. And of course, rho is the same, which means the pressures must be different because the heights are going to be the same. And so when we look at this equation, what happens here is you get a situation where if we look at P1 plus half rho V1 squared is equal to P2 plus half rho V2 squared. Well, it turns out then that the differences in pressure will equal the difference in speeds of this fluid. Well, just mathematically here, if let's say this is V1 and it's going slower, that means it must have a higher pressure in order to be mathematically equal to a higher speed, and this must be a lower pressure, which means here that P1 must be greater than P2. And this is why when a ball spins in this direction, it would actually get pushed down, because this pressure, P1, is greater than this pressure, P2, and actually you will get spun down. The same thing would happen if you spun it to the left or to the right or even up. And you can curve it essentially by spinning it. And this is another application of Bernoullis' equation.